Hey guys, it's Mr. Behrman, and I want to show you a kind of a cool problem that was given at the APSC on Saturday as a bonus problem. If all the problems that were given by the guest speaker were too easy for you, then this one was for you. So the question was given that a block starts at the top, some height h, as shown in the picture here, and that height is just enough for the block to barely make it around the top of the loop and come down on the other side on the bottom. And there's some problems we've done kind of like that, and some questions that could be asked about that. But the question that was asked at the APSC, which was a little bit different than normal, is what is the maximum angle, I want to draw it in here, theta. What is the maximum angle theta that could be removed from the track? Actually, I'm gonna put it on both sides. We'll make it symmetrical. So there's actually 2 theta here. What is the greatest portion, I suppose, of track that could be taken out and have the block still make it to the other side of the track? So if we were to remove, say, this portion of the track, could the block still make it? Obviously it would be in free fall as it reaches this point right here, and then do some sort of parabolic arc. But that was the question. So let's see if we can't figure that out. It is a little harder than I thought that it was going to be. So we'll do it one way, and then I might have a separate problem for you guys to do. Okay, so a couple of things. I'm going to say that this is the minimum height. Okay, so we're going to call this H minimum over here. And that tells us a couple things about this point. I'm going to call this point A. I'm going to call the point that the block would enter free fall point B. And at point B, or sorry, let's say at point A, assuming there was a track, we know that the only force acting on this would be the weight of the block, because the normal force would be 0. That's a qualification of the minimum velocity that we've talked about. Any greater speed and there would be a normal force. Any smaller speed and the block would fall away from the track. So at the minimum speed, n equals 0. We also know that the sum of all the forces has to be mass times acceleration. That's going to be centripetal acceleration, because this is a circular motion problem at this point, since the only force acting on it is the weight. That is mg equals m, and I'm going to put in v squared at point A over r. The masses cancel, and I get v squared is gr, and I'm going to leave it as v squared for reasons that's going to become clear later. For those of you that are clever, you might say, oh, v squared, that has to do with kinetic energy. And you're right. So that's kind of our starting conditions. Let's move on. I'm going to circle this, because that's going to come back up later. Okay, so for the next part, I'm going to use the conservation of energy. Okay, that's going to be my starting point, and I'm going to let the height at point B be my 0 reference line. You could just as easily choose the ground for this. In fact, that might be a little more obvious to people, but because I'm going to give you a different problem to do later on, I'm not going to do that. So I'm going to call this height right here 0. Okay, I'm going to go ahead and make a dotted line all the way across there. Okay, so again, we're pretending that the track above that blue dotted line is gone, and we need to find what that angle theta is. Okay, so that means that the potential energy at point B is 0, and so I can say that the kinetic energy at point B, so that's the initial kinetic energy it has at point B, is equal to, at point A, if I choose point A to be my final point, it's going to have kinetic energy at A, and also a little bit of potential energy at A, because as you can see from the diagram, point A is above point B. Now exactly how much potential energy? Well, this whole distance in the diagram is R. Okay, and you can see that we've got a right triangle here with theta as one of our angles. Okay, and the height above our reference line right here, that's the height at point A, right? Okay, so that is going to be the total radius R minus this portion here, which is the cosine part of that leg. So go back to my blue here, and I'm going to start substituting in 1/2 mvb squared is 1/2 mva squared plus m times g times the height at A. Okay, so 1/2 mvb squared is 1/2 mva squared. You can still see at the top right of the screen is equal to gr. So I'm going to go ahead and plug gr in there. Plus m times g times in here, I'm going to do a little substitution. The height at point A is going to be the total radius of the circle minus the radius times the cosine portion of that triangle. Okay, I'll let you zoom out and see that. Okay. Alright, so now I'm going to say that that's 1/2 mgr plus, I'm going to go ahead and factor out this r right here, 1 minus cosine of theta. And I'm going to pause right there because we've got two unknowns. We have theta and we've got the velocity at B, which we don't know. And we're going to take a clever leap right over here. I guess I'm the one that solved it, so I'm calling myself clever. I'm okay with that. Okay, the range equation. I'm going to remind you is this. It's been a long time since we've seen it, but that applies in any situation where the y displacement from start to finish for your projectile motion is 0, which, if we zoom back out here, going from point B to, I'm going to call the other side of this point B prime. Going from B to B prime in projectile motion, you can see that's a horizontal displacement of r, but the y displacement is 0 because it's returning to the same point. Okay. Now r, the distance it has to go across, is this total blue line across here that I'm highlighting right now. That is 2 times the sine component of that triangle, so that's 2 times r sine theta is equal to the speed at v squared, the sine of 2 theta, all over g. Okay. I'm going to do a trig identity to change the right side of this equation. So sine of 2 theta is another way of saying the sine of theta times the cosine of theta over g. So I can cancel out the sine on both sides. Oop, and I forgot a 2 there. There should be a 2 right there. Sine 2 theta is equal to 2 times the sine of theta times the cosine of theta. And my 2's cancel out, and I can get VB squared is equal to, we've got R times G, and I divide through by the cosine of theta, which is great because now we've got the speed at point B in terms of things we know or are looking for. So I'm going to plug this value in to the left side of my previous equation. I'm going to need to zoom in so I can write this over here. 1/2 m times vb squared, which is rg divided by the cosine of theta. And now the nice part about all my terms is that they all have an m and an r and a g, and so I can cancel them all out, and I get 1 over 2 cosine theta, which is equal to 1/2, plus this mgr has canceled, so it's 1 minus the cosine of theta. Simplifying, I've got 1 over 2 cosine theta is equal to 3/2 minus the cosine of theta. The problem is you can't combine those cosine theta terms because one's the denominator of a fraction and one's by itself in its own numerator. The trick here is to multiply the entire equation by the cosine of theta. So if you multiply both sides by the cosine of theta, it cancels out on the left. You get 3/2 cosine theta minus cosine squared theta. And I'm going to clean this up too. As I don't like fractions, I'm going to multiply both sides by 2 as well. So I get 1 equals 3 cosine theta minus cosine squared theta. And that kind of looks like a mess. And it is. But if you look at it closely, your variable here is theta. The terms with theta follow the pattern of squared. So to the second power on the right side. In the middle you got to the first, and then to the 0 power on the left side with 1. So you can rewrite this as cosine squared theta. Oh, I forgot a 2 there, didn't I? Should have said something. Equals 2 times cosine theta equals hold on. Sorry. Minus 3 cosine theta plus 1 equals 0. And if we let cosine of theta equal what you're probably more familiar with here is x, you get 2x squared minus 3x plus 1 is 0. This is just a quadratic formula. Plug this into your quadratic formula. I cheated. I used an online calculator for it. And you get x equals 1, or I suppose, x equals 0.5. So that means that the cosine of theta, and we're almost home here, is 1 or 0.5. If you take the inverse cosine of both of those, theta equals 0 degrees, or theta equals 60 degrees. 0 degrees is a fine answer because that would mean we take no track out, which is the original situation that we were talking about. It makes it perfectly around the loop. 60 degrees is the answer that we're looking for. That is how much track we can take out. So 2 theta is the total amount of track that we want to take out. Scroll up past all of our gorgeous math. There it is, 2 theta. Each one of those thetas is 60 degrees. So final answer, 120 degrees. Thanks for watching.